Okay, so here we are now in the last part of calculating per units. Find this value. Here 220 by 200, it is 1.1. 1.1 whole square is 1.21. 1.21 into 0.7125. Find it. 0.7125 into 1.21. Hello?
Hi, Star. Yeah,
Uh,
I'm doing. I'm doing.
0.7125. Okay.
0.7125 into
This 1.21 is total fraction. I think Satish,
point.
you have calculated, right?
Yes, Abhilash.
Can you tell them the answer?
Just a minute. 0.862125.
0.86213.
Okay. Here 0.35 into 1.21.
0.4235.
0.4235.
Mm.
Okay, so we have done the per unit calculation for positive sequence, negative sequence, and zero sequence. Now let
Yeah.
us draw the reactance diagram. First, zero sequence reactance diagram we will draw.
Okay.
For zero sequence, first we have a generator. So let us keep a voltage source with any reactance of generator. Let us check what is the reactance. Zero sequence J 0.05. Here it is J 0.05. And then we have a transformer 1. This is the first bus bar. Okay. After the transformer, we have a bus bar. So here we have a transformer 1 corresponding. What is the value for transformer 1? It is J 0.1. Similarly, for generator 2 also, the other end of the generator is grounded. So here also, this is generator 2. The corresponding is also same, J 0.05. And then transformer 2. Here also it is J 0.1. Then here we have the first bus bar. This is the bus bar 1. And here we have the bus bar 2. Between bus bar 1, bus bar 2, we have a line L12, which per unit value is J 0.363. J 0.363. And here we have the third bus bar where the fault is occurred between 1 and 3. J13, what we have, what value? It is J 0.4235. J 0.4235. 4235. And between 2 and 3 also we had a line. So this is between 2 and 3. And the corresponding impedance reactance value is J 0.8621. J 0.8621. Now, if we see in the previous discussion, we have seen that whenever we are using Thevenin's theorem, Thevenin's method for the finding Z effective or XTH, we need to convert that circuit into two parallel branches. If we have seen, let us recap. Whenever we should convert the circuit into a circuit like this, free fault voltage with the fault impedance ZF, and then we should have two parallel branches. Two parallel branches. One branch should be having a. Here, if we observe what are the synchronous machines in this problem, we have two synchronous generators, alternators. So the first branch should carry the current from the generator 1, that is I1, and the second branch should carry the current from generator 2, that is I2. So whenever we are doing this Thevenin's method, we should convert the circuit. Whenever we are trying to solve this, find the Z effective or XTH or XTH, ZTH, we need to convert that reactance diagram into a circuit like this. So here, if we observe, this is the equivalent circuit. Now, if we want to convert this, here we have first bus bar, second bus bar. So we need to convert this delta into corresponding star. So we should convert this delta to star. How to convert this delta to star? Here, this is equivalent circuit in star. Let me take this is A and this is B. The value of reactance between AB is J0.363. 0.363, and the value of reactance between here it is C, AC is nothing but J0.4235, 0.4235. Similarly, the value of reactance between BC is J0.8621. J0.8621. Now, when we convert this into star, let me take this is RA, and the side which is towards the vertex B as RB, and the side which is towards the vertex C is RC. Now, what is RA? RA is RAB into RAC divided by sum of all. RA is nothing but RAB. Find this RAB into RAC divided by sum of all. That is RAB plus RAB, BC plus RAC. So if we want to find this RA, then what I should do? 0.363 into 0.4235 RA, which is equals to J0.363 into J0.42 J0.45 divided by sum of all, that is J0.363 plus J0.4235 plus and the other impedance is J0.8621. J0.8621. Find this value. Numerator and its denominator, if we find separately, the denominator will be same for all the parameters. So we can find numerator and denominator separately.
Numerator is 0.15373.
15373.
373.
Okay.
Denominator is okay. Wait a minute.
Similarly, RB will be is equal to RBC, RAB into RBC divided by summation of all. Summation that is equals to RAB is nothing but what is RAB point?
Denominator is 1 point.
Okay, J gets cancelled.
6486.
1.6486.
Mm.
Okay, here there will be a J and numerator J square will be -1. So this is again 1 by J will become -1. So minus of minus will become plus. So plus J into find the magnitude. This 0.15373 by 1.6486.
Point 09
0.09
325.
09325. Okay. Now find this point J 0.363 into J 0.8621.
Okay.
Divided by the summation is J 1.6486. This is Thevenin's method. This is Thevenin's circuit.
0 point.
Numerator or whole value.
Whole value.
J
18 982.
0.18982. Okay, for RC, what we need to do for RC, it is 0.4235 into 0.8621. 4235 into 8621. RC will be equals to RAC into RBC by summation. So we need to find RAC is nothing but 4235. J 0.4235 into J 0.8621.
Answer is
Divided
0.
by 0.22
146.
146.
Wait a minute, I'll be back.
Okay. J 1.6486. So now the final diagram will be this is corresponding to generator 1. Here, if we observe, these two will be in series. Similarly, these two also is there in series. So it will become J.15. J.15. Similarly, J.15. J 0.15. And here, this is the first bus bar. This is the second bus bar. Now here it is connected. The new star connection. This is the third bus bar. So here, what is this? RA is nothing but say 0.093, say 0.0985. Similarly, RB is 18982, J 0.18982. And here RC is nothing but J 0.2216 or 22146. Again, these two are in series, and these two also in series. So the series combination, if we add these two, what we will get? These two, summation of these two. We remove this. Here it is grounded, upside it is grounded. Here also, if we observe, the upside it is grounded. So the series combination of these two, if we notice, these two are in series. Here we will get one impedance, reactance.
Bus one side the sum value, series sum value is 0.2
Okay. 0.2
4325.
24325. 2432. Let us take for 4 significant digits. Okay. Here this side
898. 0.3398.
3398. 0 point. Okay.
Yeah, 0.3398.
0.3398.
98, yeah.
So now these two are in parallel. So find the parallel combination R1 R2 by R1 plus R2. Here it is again J 0.2214. This is the bus bar 3. These two are parallel here. Parallel combination.
0 point.
Complete parallel combination. Okay. 0 point
14
0.14
175.
17
5
17
17, that's right.
is in
Plus
series 2214.
0.2214. 0.36.
The final value of XTH is nothing
Yeah,
but XTH. Let me represent for zero sequence. So XTH 0.
0.
What is the value?
0.3631.
Wait. 1 minute. Here there is the ground. This is the ground. And we know between the fault, here there is a fault point is at bus bar 3. So between the fault and between the bus bar, as we have seen here. So this in this diagram, is we see now, this is actually this. Okay, here we have pre-fault voltage. This should be actually fault point is connected to negative of pre-fault voltage V0. If we see the previous symmetrical fault analysis using the Thevenin's theorem method, the fault point should be connected to the negative terminal of pre-fault, negative terminal of a voltage source, which voltage of pre-fault voltage, and the positive terminal should be connected to ZF. ZF and the ground. This is ZF. And in question, they had given here it is the positive. ZF is nothing but Z.1. Z.1. Where is that? Yeah, Z.1 per unit. ZF, which is equals to Z.1 per unit. Z.1. So, what is the Z XT not? XTH, what is this XTH?
0.36.
Z.36.
315.
36315. Now, if we want to find the, okay, let us keep like that. This is the XT naught, XTH for the zero phase. And then we know the ZF is Z.01. And in this problem, since they had not given any terminal, if they had given load, then based on the load, we will be finding the pre-fault voltage, which is nothing but the terminal voltage across the load divided by the base value. Since they had not given, the pre-fault voltage is nothing but 1 per unit. So 1 at an angle 0 per unit. Assumption this is, if they had not given the terminal voltage, we need to assume the pre-fault voltage like this. Current flowing through this is fault current. From this fault points and from to this ground, the fault current will flow. Whenever there is a fault, the fault current flows from the fault point to the ground. The current flowing through this fault current IF. So this is assumption, assume. Okay, now let us go to next, positive and negative sequence. This is corresponding to zero sequence. We complete till here for positive and negative sequence also. Then all four subdivisions are just formula substitution. Now let us go to positive and negative sequence diagrams. Actually, both are same. Positive is nothing but x1. Which is equal to negative. Here in this problem, negative sequence is also negative. Which is nothing but x2. Sequence. Okay, now if we see, let us draw the reactance diagram for this case. Initially, we are having a generator. So the generator directly, I'm removing the generator voltage source. Or else let us draw in the reactance diagram. When we are drawing the Thevenin's equivalent circuit, we will short circuit this. This is the reactance diagram. When we are drawing the Thevenin's equivalent circuit, this is corresponding Thevenin's circuit. Circuit will always should have two parallel branches. The current flowing through parallel branches should be from the synchronous machine. If there are one synchronous generator and synchronous motor, then one branch will take the current from synchronous generator and another branch will take from synchronous motor. If there are both synchronous generators, each branch will be taking current of the synchronous generators, as this case. So this is the Thevenin's equivalent, Thevenin network. When we come to Thevenin network, we will be short circuiting these voltage sources as we have discussed. After Thevenin's network, then we need to excite this Thevenin's network with pre-fault voltage. That also we have discussed. Okay. Now coming to here, generator 1 corresponding reactance, and transformer 1. Here we had the first bus bar 1, and similarly the other end is connected to the ground. Here it is generator 2 corresponding reactance, and then transformer 2. It is other end is connected to the bus bar 2. Between bus bar 1 and bus bar 2, we are having a reactance, and then here we have the third bus bar. Here there is some reactance 1 and 3, between 1 and 3. Similarly, there is one reactance between 2 and 3. Here there is a fault. Here we had a fault. And the topmost, it is grounded. This is grounded. Okay, now coming to, we are going to take the values of positive and negative sequence. So positive and negative sequence 0.15, 0.15, 0.1, 0.1. A 0.15. Similarly, this is also J0.15. And for the transformers, it is 0.1. So J0.1. Similarly, here also it is J0.1. And now between line L12, what is the value of L12? 0.1512. Say 0.1512. And between line 1 and 3, what is the value? We see 1 and 3, it is 1815. This is J0.1815. J0.1815. Here between 2 and 3, 3025. Say 3025. J0.3025. Now find the corresponding star values. If we want to get here resistance, multiply, first take the sum of all these three and write there. So what I'm doing, these two are in series. Similarly, these two also in series. And I'm replacing the star with corresponding delta. Here you will get a reactance. And then here you will get one more reactance. And here you will get one more reactance. If I read right, here it is J0.25. J0.25. Similarly, here it is J0.25. J0.25. And then the other end of the generator is grounded. So we can connect this to a common ground. This is grounded. Here we have the first bus bar 1. And here we have the second bus bar 2. Now, here we should get the corresponding star equivalent. This is the third bus bar where the fault is occurred. Here we had a fault. So here, this corresponding, we take this as A, and this is B, and this is then this A will be is equal to, like previous case, J0.1815 into J0.1512 0.1512 by summation. What is the value? Similarly, this B will be say 0.1512 into yes, J.325. 3025 is. Oh, wait. 3025. Am I correct? It is 3025, I guess. Yeah, it is 3025. 0.3025.
Akhilesh, first I'll
So
say
the
denominator first.
okay, this will be changed as I have changed this. Check it.
Yeah. 3025 only I have kept.
Okay, what is this summation value?
Summation is 0.6352. 6352.
0.6352. Okay. Okay, Z into 3025 by.
Okay, then now
You tell me the first
0.1512 into 1.1815 divided by 0.6. Hey, where is the summation value? 63?
6352.
6352. So the answer is 0.0432.
Z 0.04. 0.40432. Okay. Now you find B value.
Wait a
Similarly,
minute.
what will be my C? And let me read C expression. C is equal to, it is J.1815. Say
0.1512 into 0.3025 divided by 0.6352. 0.07
value or only numerator?
overall value.
Okay, J 0.07.
0720.
20. Okay, now you find C, which is equal to J 0.1815 into J 0.3025.
25. Wait a minute.
3025 divided by
0.3025 into
J 0.1815.
0.1815 divided by 0.6352. The answer is 0.08.
Wait, 0. J 0.
0864.
Okay, 0.864. Okay. Now again, if we see these two are in series and these two are in series. These two are in series. Now let us draw the equivalent diagram of the series combination. You take these values 0.25 plus point. Okay, it will be 0.2932 here. So one parallel branch, it is J.2932. And the another parallel branch, what it will become? 0.25, 0.3220. Yeah, some of these two, 3220.
3220, correct.
Parallel with, you find this parallel combination 0.3220.
Wait a minute. 1 second.
Upside it is connected to the common ground.
0.29. 0.32 into 0.3220 divided by 0.2932 plus 0.3220.
Downside
0.153.
86. Right? Point, say point
153
153.
4.
Okay. 1534 in parallel with J 0.0
In parallel or in series?
series J 0.864. 0.0864. Here it is J 0.864 and here it is ground. Yes, yes, whether I had drawn. Okay. This is the ground. And here the third bus bar where the fault occurred. So we will be having is my ZF. And here this fault point is connected to the negative of the band. The current flowing through this fault current IF. These two are in series. What is my final answer?
Series
XTH1, which is equals to XTH2.
8, 9 plus 3. 2, 3, 9, 8.
XTH2, which is nothing but J 0.2398.
Yeah, 2398.
J 0.2398.
Yeah.
This is fault current, okay, and here also ZF is J.1 per unit. ZF is nothing but J.1. J.1 per unit, and then my pre-fault voltage V0 is 1 at an angle 0 per unit. So with this, we have done everything. Now let us go to the computation. Some disturbance. Okay, now it is clear. Till now we have seen how to, we have done everything. We have draw the reactance per phase. First we have done the per phase per unit analysis. Then we have found out this reactance diagram. Then we have found out this ZTH. Now let us solve this problem. First subdivision. What is first subdivision? Three-phase fault is occurred at the third bus bar. What we need to do with that? When the three-phase fault is occurred at the first, okay, we need to find out the fault current. Fault current is my final result, what it is needed. So let us find out the first subdivision. Okay, first is three-phase fault. For three-phase fault, fault current I need to find out. Fault current expression IF. Fault current expression IF in per unit. In per unit is equal to pre-fault voltage in per unit divided by XTH plus ZF. Now here we have two different XTH values also we have found for a zero sequence, positive sequence, and negative sequence. So when we are considering this three-phase fault, what we need to take? We need to take the XTH value of either generally when three-phase fault is occurred. And if we want to compare this three-phase fault with the each fault, positive sequence, negative sequence, zero sequence, the positive sequence is equivalent to the three-phase, general three-phase fault. So what we are going to do here, this is nothing but XTH1 we need to consider. XTH1. Okay, wait 1 minute. There is some mistake here when we are drawing the zero sequence diagram. Okay, wait, where is this? Okay, wait. First, let us complete this. What is this? So, what we are getting? Old per unit value is 1 divided by XTH1 is nothing but say 0.2398. Say 0.2398 plus say 0.1. Find this value.
J
0.2398 plus say 0.1.
plus
Yeah. XTH plus Z.
J. Yeah, that is J 0.3398.
2398.
No, the sum is 3398.
Okay, this is 3398.
Yeah, plus 0.1 only na.
Okay, you are telling the whole answer.
Yes, I'm giving. Divided by 1.
Invert it. 1 by.
That is 2.94. 2.942.
2.942 minus J you will get, since it is 1 by J minus J.
Minus J 2.9429.
Now convert this into polar form.
Polar form, huh?
This is in rectangular form.
Polar form, it is same 90 degrees. Same magnitude, 90 degrees.
Same magnitude.
Yeah, same magnitude, 90 degrees.
2.9429
Plus
minus 90 need to get.
Plus 90 only, because it is minus J.
Type A minus JB. This
Yeah, it's
0
minus
minus
90. Right, it's minus 90.
magnitude also will vary. Once check it. I think
Minus
magnitude
2.9429.
0 minus 2.9429 I shift plus or minus.
Wait 1 minute. 9429. I shift
plus
same magnitude only, bro. Same magnitude, minus 90 degrees.
Okay, 2.9429 at an angle of minus 90. Yeah.
Yes.
Okay. This is the fault current in the first case. While going to fault current in the second case, we have done one mistake in this problem. Let us correct. Especially, we need to revise one thing. For drawing the zero sequence diagram, we had a rules. Based on the transformer connection, we need to replace with some other circuit. Zero sequence transformer connection.
Yeah, something they have given, right?
Zero sequence transformer connections. So it is very important to notice what is the connection given for the transformer whenever they have given. We had one tabular form for different connections of transformer. We need to replace with corresponding circuitry. We have one tabular form. Let us just revise that. If the transformer connection, this is the transformer. If the transformer is connected with star with the neutral grounded on primary side and star with the neutral grounded on secondary side, then the diagram we need to replace is, it should be replaced with like this, A and A dash. A and A dash with a ground point. This is the ground, common ground. That meaning is actually what is this A and A dash means? The primary and secondary side corresponding A phase circuits. If the fault is in the A phase, let us assume unsymmetrical fault. If it is A phase, this is A, this is B, and here it is C. And the neutral point is grounded. Similarly, on the secondary also, we will be having, this is A dash, and the another phase, B phase is B dash. This is B dash, and here we have C dash. Here it is grounded. This neutral point is grounded. This is actually the primary and secondary. This is the primary. This is the secondary of the transformer. Circuit diagram. And this is the zero sequence diagram. Zero sequence diagram is this one. So it should be replaced like this. Whenever there is the connection, like one side there is a star with neutral grounded. One side we are having star with neutral grounded. On the other side, we are having just a star connection. Then corresponding circuit will be, here we need to give a gap. This is A dash, and here it is A, and here we have a ground. This is the ground. Then, suppose the connections are one side there is a delta connection, one side it is star with the neutral grounded. Here it is star with the neutral grounded. This is star with the neutral grounded, and here we have a delta connection. Then the corresponding diagram will be like this. This is A dash. This is A, and here it is ground. If one side it is star connected, on another side it is delta connected. Here it is star, here it is delta connected. Then the corresponding equivalent circuit will be similar to star with neutral grounded and a star. That is A. Here you just use some gap. And here we need to remember these 5 connection diagrams to draw the zero sequence circuit, especially the transformer based on the transformer connections. And the last case is if both sides we are having a delta connection. If both sides we are having a delta connection, then the corresponding diagram will be here it is A dash, here it is A, and this is the ground. At both ends it is connected. So now we need to modify it. So if we see this, what are the connections? In primary side, both sides it is star with neutral grounded. So the primary zero sequence diagram, let us go to the zero sequence diagram. So we can directly, this connection is directly, since both sides it is star with neutral grounded, it is correct. Star with neutral grounded and star with neutral grounded. Based on connections, we need to draw here. That is the small mistake we have done. Let us correct it now. Both sides it is star with neutral grounded. And what about the transformer T2? Transformer T2. It is star with neutral grounded and delta. Coming to this one, this J0.1. This is a star with neutral grounded. This is connected like star with neutral grounded. Star with neutral grounded is the secondary actually, and delta is the primary. Flash. This is the connection diagram. So this is the secondary, this is the primary. Here both are same, so no need to worry. So when both are star with neutral grounded, which case it comes to? Both are star with neutral grounded, first case. That is directly we can join, no issues with that. When one side is star with neutral grounded, another side it is connected to the ground. It is connected to the delta. Then what is my equivalent circuit? This is my equivalent circuit. So here not this case. Here it is correct only. This is positive sequence. We need to go to zero sequence. So in this diagram, here there will be a break in the circuit. And this end is connected to the ground. So this is connected to the ground here. So when we are doing the equivalent circuit calculation, we will just remove this portion. This portion is not required. Why? Because there is an open circuit. So whenever it is like this, let me draw in detail. So here, whenever this is the case, then it will be equivalent to a break, and here it is connected to the ground. And here, this is the continuation. This is the ground. This downline is the ground. And this is the side where it is star with neutral grounded. Star with neutral grounded. And this is the side of delta connection. Since here, this side it is delta connected, and here to the side of secondary bus bar, it is star with neutral grounded. This is A, and this is A dash. This is A dash. So this is my A, here it is my A, and here this point, this terminal point will be A dash. This terminal point will be A dash. So this total corresponds to transformer T2. Here there is no issue. Why? Because whenever there is both sides, it is star with neutral grounded, it is a direct connection between A and A dash. And this is my ground. So this is my A, here it is my A, and this is my A dash. This point is my A dash. Both sides, it is here also it is star with neutral grounded, and this side also it is a star with neutral grounded. Here also it is star with neutral grounded. So when this is the case, now what is the changes in the equivalent value we will be getting? Only we need to change this J.15 to J.1. So let us change here. Here alone we will be getting J.15 should be replaced with J.1. So this is J.1. Now if we see what is the series combination of this, it is 2898. So this will be changed to this is 2898. 2898. Then what is the parallel combination of these two? Hello, am I audible?
Yes, Akhilesh.
Hello.
Yeah,
Okay,
you're
can you
audible.
find the parallel combination of 2898 and 2432?
Just a minute.
Is 0 point. Okay. This is the fault point. Two eight nine eight and 2432.
2892.
2898 and 2432. You just R1 R2 by R1 plus R2.
Yeah, 0.132.
0.132.
Yeah, 13223.
1322. Now the series combination of these two.
0.2214. 0.3536.
So this is the 3536.
Yes.
So this is the change actually. We forgot about this. This is the change we need to implement when we are drawing the zero sequence impedance.
Okay.
So now we have completed the first subdivision, that is three-phase fault. Now let us go to the second subdivision, that is single line to ground fault. Second one.
Single.
Division is,
Yes.
yeah, LG fault. LG fault. So when we come to LG fault, we need to revise what are all the equations to solve the fault current. For LG fault, if we see the current, we have the equation that I is equals to voltage, especially at the third bus bar. Since the fault is at the third bus bar, I3 is equals to V3 of 0, that is terminal pre-fault voltage divided by XTH1 plus XTH2, that is positive sequence equivalent, Thevenin's equivalent, plus negative sequence Thevenin's equivalent, plus zero sequence Thevenin's equivalent, XTH0 plus ZF. This is the equation ZF. You may get a doubt that this is the fault current. For all the fault current also will be having the zero sequence, positive sequence, negative sequence. So this is the fault current for zero sequence. This is same value will be the fault current for positive sequence, I31, and the same value will be for I32 also. So the positive sequence, negative sequence, zero sequence fault currents for LZ fault will be same, which is equal to the pre-fault voltage. This is it. Yeah, I3, that is fault current at the third bus bar. Fault current IF in per unit. The answer which we get is the fault current in per unit. Okay, now what is the pre-fault voltage? Pre-fault voltage is 1, which is equals to 1 divided by XTH1 and XTH2 are same. So I am writing 2 times of what is the XTH for first 1 and 2. That is J0.2398, J0.2398, 0.2398. And for zero sequence, we have just now updated the Thevenin's equivalent voltage, the Thevenin's equivalent impedance, that is J 0.3536. J 0.3536. J 0.3536 plus J 0.1. That is Z. Find this value. Here also it is, we can write this as I3 fault current. That is I.
Akhilesh 1.9332.
1 minute. Default voltage also we should take at the third, which is 1.9332
కాదు కాదు ఒకసారి అవ్వ.
minus J.
అఖిలేష్ 0.9332 వచ్చింది. 1 divided by
0.9332.
0.9332.
1 divided by 0.9332. Final answer 1 divided by 0.9332.
1.071.
J minus J
0715.
1.0715.
Hmm.
Convert this into polar form, rectangular form.
Polar form 1.0715.
0 minus 1.0715 I shift plus.
Okay.
This,
0.075 angle minus 90.
1.0715 at an angle of minus 90. Now, what is this? This is actually the fault current for positive sequence, zero sequence, and negative sequence. This is for fault current for all the three sequences, sequence components of fault current. But what we need to find out, we need to find out what is the fault current in each phase. A phase, what is the, here what we got is sequence components of fault current. Now we need to find out what is the phase current, that is in A phase, what amount of fault current, phase components of fault current, phase components of fault current I3, of IF3, I3 in bracket fault current. Now we have a relationship between the fault phase components and the sequence components. We have a matrix relation between these two. That is, now what we need to find is I3A, I3B, I3C. We have a matrix I3A, that is A phase. The fault, the third bus bar current is a three-phase current. A phase, how much amount of current is flowing? In B phase, what is the amount of current is flowing? And C phase, what is the amount of current is flowing? I3C. Which is equal to, we have matrix 1, 1, 1, and then 1 alpha square. What is the value of alpha?
1 angle 120.
Okay. 1 alpha square into sequence components, all three are same. Just now we have seen, no?
Yeah.
Into, actually this matrix expression is with respect to zero sequence only.
Okay.
Wait, is this zero sequence or all the sequences?
All the sequences, right?
I3 1, and then
And then
here I3. Now all the sequences are equal. Just now we have calculated. So the value of this is, let us take here alpha. If you take one at an angle of 120 degree, you need to take this. This
okay.
as the value. If you take the alpha in rectangular form, what is the value of alpha in rectangular form? If you convert 1 at an angle 120,
1 angle 120 in rectangular. Minus 0.5 plus
minus 0.5.
plus 0.866 I.
Okay. Better to do in plus 0.866. Better to do in polar form.
Yeah.
Okay. Now, if we substitute this J, in this problem, since all the three are equal, that is I3 of 0 and then I3 of 1, I3 of 2 are equal. So, what we can do this 1, 1, 1, 1, 1 at an angle of 120 degree. Alpha square, I think 1 at an angle of 240 here.
Yes. 1 at the angle of 240.
Yeah, 1 at an angle of 240, 1 at an angle of. And again, here it is 1 at an angle of 120. And finally, 1 at an angle of 240. Okay, now here if we see, when all the elements are equal, what can we do? When this all three are equal, can we simplify it instead of writing everything in that matrix?
Yeah.
What can we do when all the three are equal? Can we take common?
Common is 1 and goes. 1, 1, 1.
I'm also not sure about the matrices. I didn't remember also 1.0715. 0715. Now, how to solve this matrix at an angle of minus 90? So I think what we will get 1 into this element into this element. Here also same.
Ah.
So the final matrix will be, let us consider this element 1 into this 1 at an angle 1.0715 at an angle of minus 90 degree. Again, this second element is multiplied with this second element. Right?
Yeah.
So I think you will be getting three times when we add this.
Yeah. 3 into 1.075.
Yeah, final answer will be that. Okay, then what about here? Again, 1 into this.
Yeah, but the second one will be multiplied with 1 angle 240.
You try to get that answer final matrix possible.
Just a minute.
First to find three times of this. I think we cannot directly multiply the magnitude with 3. One here it will be same. First to find 1 into is that only, obviously. 1 into 1.0715 at an angle of minus 90.
Akhilesh, could you tell me the values, like the first one? Okay, no problem. I'll calculate.
3 into 1.0715 at an angle of 90. Just to take 3 into.
Yeah, I'll take no problem.
Take bracket. Take bracket 1.075 angle will be there. If you take shift somewhere, so at an angle of minus 90, you will get one magnitude. Shift equal to and you see rectangular form. First, you will get rectangular form when you do this. Else, let us leave these answers as such. Let us see the procedure.
Okay, no problem.
Why? Because there will be still many calculations.
Matrix multiplication, right? 3 into 3 into, matrix into 3 into 1 matrix.
Yeah. Later on, I will fill this and I will send you.
Okay.
Now, this is the procedure for finding the phase components of fault current. Now, let us go to the next subdivision. What is the third subdivision? Next case.
Double line ground. Sorry. That's line to line.
Line to line fault. Next is line to line fault. LL fault. If we want to find for LL fault, we have line to line fault. We have for equations. First, final equations for the fault current in line to line fault is in the third bus bar node. So I3, we need to find out I31, which is equals to the formula for the LL fault. I31 is equals to minus I32, which is equals to V3 default voltage, V3 naught divided by again XTH1.
Atleast presentation ఆగిపోయింది. Hello,
am I audible? Is my screen visible?
Screen stuck అయిపోయింది.
Oh, wait. I will stop sharing and start again. Now is my screen visible? Hello, now is my screen visible?
No, Akhilesh, not yet.
Let me stop once and start sharing screen again. Now is my screen visible? Hello, is my screen visible now?
No, Akhilesh, no. Still it's showing blank screen.
Let me rejoin.